Hello class, today we're covering lesson 4 in chapter 8, zero and negative exponents, and we have here an illustration of a piano and its keys, and we read, when a piano is tuned, the first note to be tuned is the A above middle C. After it has been tuned to a frequency of 440 cycles per second, the rest of the A's on the keyboard are tuned so that each successive A has twice the frequency of the one before it. This means that the three A's above middle A are tuned as shown here. So we have 440, and we're going to multiply that by 2 because it's twice as much. So let's put our 440 as they're writing it on the textbook. And that's going to be equal to 800. Or let's see, first 440 times 2 to the first power, okay, and that's going to be equal to 880. Now notice we also have 440 times 2 times 2. So we could illustrate that here. Times 2. Now that would be equal to 440 times 2 to the second power, or 2 squared. Okay, that's a 2 down there. Oh, I'm starting to look like a 3 now. Okay, let's write it well. And that's going to be equal to 1760. And then the third one, we have 2 times 2 times 2, or 2 to the third power. So we have 440 times 2 times 2 times 2. So they just keep doubling. And as they double, we notice that what we're doing is we're raising, and here's what we're learning here, is that we're raising to a one power, the base of 2. So we're saying 2 to the first power, 2 to the second, and 2 to the third. And we see the result here. We're getting a doubling effect. So so we now have 440 times 2 to the third power. Now let's just turn over and take a look. From the middle column of this table, it looks as if a formula for the frequencies of these notes is 440 times 2 to the n power. So that would be the formula in which n is equal to 1, 2, and 3, right? So we're going to put a variable in the exponent. So let's go with 440 times 2 to the nth power, okay, and we saw that n in this case was equal to 1, then it was equal to 2, and then it was equal to 3. So we just plugged in this value here, and we created these values, all right? Now, if the keyboard continued, it would seem reasonable, or it seems reasonable to assume that the formula would continue to work with n is equal to the 4th, 5th, 6th, and so on. Now, what would happen if we try applying this formula to middle A itself? Because the integer before 1 is 0. So now, what would we have? Well, we have 440. Let's write it on here. 440 times 2 to the 0 power. Okay, well, we would have 440 because we know anything to the 0 power, would that not be itself? Well, let's prove it here. Because if we see what we're doing here, we're actually dividing. Actually, we're doubling. I'm sorry. The doubling effect is going on here. Everything is getting double because we're multiplying by 2, right? So it's 2 times more. And we see the first 2 here, 2 times 440 is 880. Then 2 times 2 times 440 is 1760. So we're simply adding, right, a 2. Okay, in each case we're adding a 2, or I'm sorry, when I say we're adding a 2, we're adding it to the factor as a factor. So we're multiplying by 2, and we're just simply doubling. So we could also say the same if we were to go backwards. Okay, if we were to actually go backwards, what would we be doing? We would be dividing by 2, wouldn't it? So as we remove a 2 and we reduce this exponent by 1, we're dividing by 2, right? So we take 3520 divided by 2 would be 1760. And that's as if, again, we're removing one of the factors of 2. So if we did it up here, same thing would happen. 1760 divided by 2 would be 880. So we're going to remove another 2 here, and what that means is we're going to divide, and it's going to come out to 440. And again, we're not dividing, but we're kind of just showing you the logic. If you're going forward and you're increasing this exponent by 1, which means basically you're just multiplying by 2, okay? So you had 2, and then 2 times 2, and you add another 2, 2 times 2 times 2. So we're just going backwards now. And we know that 2 to the 0 power is equivalent to 1, because the only thing we could actually multiply 440 by to get 440 would actually be 1. So 2 to the 0 power is equal to 1. And this is a good way to show how 2 to the 0 power actually equals 1. Anything to the 0 power is equal to 1. Now, what happens if we were to continue and go into negatives? Okay, applying the formula to the a's before middle a would require the use of negative integers. So now we're going to go into 440 times 2 to the negative first power, and we have 440, oops, that 4, times 2 to the negative 2 power. And then we're going to go 2 to the negative 3 and 2 to the negative 4. And you're going to see the effect that I just illustrated. Oh, that's a negative 3 and 440 to the negative 4. And if we apply the logic that I just showed you where we were actually dividing by 2, look what's going to happen. We're going to get, what's half of 440? Well, that's 220, okay? It has a halving effect. When I say halving, I mean with an L. A halving. All right, you're cutting it into halves. Okay, I don't know if that's a real word. Let me just take it off there before the English teachers. But we're basically just cutting it in half. Okay, I'm sure it is. Now let's see. 220 divided by 2, that would be 110. Okay, so 440 times 2 to the negative 2 power would be 110. And then if we did it again, this would be 55. That'd be 2 to the negative 3. And 2 to the negative 4 is 27.5. Now, it would be very difficult for us to just come up with this number. If we were in the middle of a problem and I came up with 440 times 2 to the negative 4 power, I just took a simple way of dividing by 2, right? We were dividing by 2. So you're not going to be expected to be able to do that. Go back and figure out. I mean, you always can. But we should know that there is a way that we can look at this. If we keep reading, it says, because it doesn't make any sense to think of 0 and negative exponents as meaning repeated multiplications, okay, we will have to figure out their meanings from these equations instead. Okay, if 440 times 2 to the 0 power is equal to 440, then it follows that what we want 2 to the 0 power to equal 1, all right? And if 440 times 2 to the negative first power is equal to 220, then it follows that we want 2 to the negative 1 power to equal 1/2, because we basically cut it in half, okay? And in the same fashion, if we look, 2 to the negative 2 power is equal to 1/4, or 1 over 2 to the 2 power, okay, or 2 squared. 2 to the negative 3 is equal to 1/8, or 1 over 2 to the 3rd power. And 2 to the negative 4th power is equal to 1 over 16, or 1 over 2 to the 4th power. So if we continue reading here, it's because it doesn't make any sense to think of 0 and negative exponents as meaning repeated multiplication. We will have to figure out their meanings from their equations instead. Now, if 440 times 2 to the 0 power is equal to 440, then it follows that we want 2 to the 0 power to equal to 1. So in this case, we can see this is 440 times 1 would equal to 440. So 2 to the 0 power would equal 1. Now, if we come down to here, we would want 2 to the negative 1 power to be equal to 1/2. Why? Because we would multiply 440 times 1/2 to get 220. Now that means 2 to the negative first power would be 1/2. And if we continue down and we look at these, 2 to the negative 2 power would have to be 1/4. And 2 to the negative 3 power would have to be 1/8. And why am I saying that? Because these are the numbers that you would have to multiply 440 to get the result that you're getting. Okay? So it means that 2 to the negative 1 power is equal to 1/2, 2 to the negative 2 power is equal to 1/4, 2 to the negative 3 is 1/8, and 2 to the negative 4th is 1/16. But we can also see a trend in this that we're spotting. It would be 1 over 2 to the first power. This would be 1 over 2 to the second power. This would be equal to 1 over 2 to the third power. Sorry, that's a 3 there. And this would be equal to 2 to the 1 over 2 to the fourth power. So we can see a pattern here. Okay. If we take a look, what's happening is that we can represent, and this is what we're going to cover in the next page, but we can actually represent a negative exponent in such a way that we will take the negative exponent over here and we will divide the base into 1 and then put the exponent here. So you notice that that's what's happening. The negative 2 is coming here, it's becoming positive, but it becomes 1 over the base, which in this case is 2, 1 over 2 to the second power. This is 2 to the negative third power. Notice the 3 is down here. It becomes positive now. So 2 to the negative fourth power, okay, is now 2 to the fourth power. Sorry for the really small print there or writing, but you can see what we're basically doing is that when we turn over and we have x to the negative a power, I'm going to write this down. We'll go over the example at 5, but I wanted to really just capture this. X to the negative a is equal to 1 over x to the a. So for us to turn this into a positive, we would take this entire expression and divide it into 1, but then we would change the exponent to a positive. So now we can see what a negative exponent does. It exponentially becomes smaller because as we were showing here that we were doubling, okay, we're doubling, and we're going higher and higher. When we start going into negatives, and again, we were doubling simply because the base was 2. Okay, if it's a different base, and we'll see that with 5, it's going to be a different number. But you can see the effect here is that it's going to now become smaller. Negative 1, negative 2, negative 3, negative 4. The effect would be like multiplying by 1/2, by 1/4, 1/8, and 1/16. So it becomes smaller and smaller and smaller. It doesn't become negative. That might be the initial thought. It's like, well, it's a negative exponent. This must be a negative number. That has nothing to do with the number itself. It's what we're doing. What's the action that we're performing on that base? And in this case, what we're actually doing is we're performing really multiplying, but we have to understand that as we go into negatives, what we're multiplying in a sense is a much smaller number, because when we were at 2 to the first power, we were multiplying by 2. When we got 2 to the 0 power, it simply became 1. So now we can only get smaller and smaller and smaller. Okay, now let's take a look here. We have this pattern also extends to bases other than 2. For example, look at this pattern of the powers of 5. We have 5 to the third is equal to 125, 5 to the second is equal to 25, 5 to the first is equal to 5. Now what you're noticing here is that you're dividing by 5. Again, the base is the division, and again, and they're not pointing this out. I just point this out to you so you can visualize it. We have 5 to the first is equal to 5, then 5 to the 0 is equal to 1, okay? Then we have 5 to the negative first power is 1/5, or 1 over 5 to the first, and then 5 to the negative 2 is equal to 1/25, which is equal to 1 divided by 5 to the second power 5 squared. So we can just continue doing this. If the exponent is decreased by 1, the resulting number is the preceding 1 divided by, or the preceding 1 divided by 5. So we're just dividing by 5. This pattern works for all bases except 0. So we can define 0 and negative integer exponents in the following way. And I already pointed out the second one. The first one is x to the 0 power is equal to 1, all right, in which x may be any number except 0. In addition, and again, we read the second one, the definition of negative integer exponents, x to the negative a is equal to 1 over x to the a, in which x may be any number except 0. Now, in addition to being consistent with the patterns we have already observed, these definitions have been even more important, or have an even more important consequence. The laws of exponents that we discovered for positive integer exponents work for all integer exponents. They are repeated here below. We have the first law, that is, if a and b are integers, then x to the a times x to the b is equal to x to the a plus b. The second law, if a and b are integers, and x is any number other than 0, then x to the a power divided by x to the b power is equal to x to the a minus b power. And then the third law is that if a and b are integers, then x to the a raised to the b, or we could have said parentheses x to the a and parentheses to the b power, is equal to x to the a times b power. And then they have some examples here, which are 0 and negative exponents. And they're simple examples how they're applied here. So it's the end of this lesson.